pose this problem, and it's similar to a problem I saw in an Olympiad prep document somewhere. I can't remember what it was. But you're given two 6-digit numbers, and you're also given that they have the same remainder when divided by the same 4-digit positive integer d. So the question is, how many possible values of d? And there's no assurance there will be any, but let's see how this goes. Now, I just do the standard sort of thing here. It's quite a bit of information to know that d is 4 digits, actually. It means that the quotients are going to be small. So I just write down two corresponding division algorithm statements right here. And what makes this fly is that when you subtract, the r's eliminate. The r's eliminate, and you get this statement right here. Okay? And again, this 6666 you see is the difference of the number 108,941 and 102,275. Okay? Now, so it's important here just to know the factorizations of 6666 that produce 4-digit divisors. So let's see what we got. You could multiply the trivial 1 times 6666, right? That certainly meets the test. So 666 itself would be one of the possibilities. But also you have 2 times 3, 3, 3, 3, like that. Okay, so that would also be another 4-digit divisor. And what else do we have here? We have 3 times 2, 2, 2. And then the last one that will produce 4-digit divisors will be 6 times 1, 1, 1, 1. Okay. Now you may say, how do you know you're done? Well, that's a good question. But notice that the prime factorization of this number is 2 times 3. And it takes a little bit of time to get this. But this helps us to prove that these are the only 4-digit divisors. So 11 is a divisor of this by a well-known alternating division test. And then you have times 101. Now, the important thing about this factorization is that each of the exponents are 1. So you can find all of the divisors, or how many of the divisors, just by incrementing and multiplying. So there's 2 times 2 times 2 times 2 equals 16 divisors. Okay. Now, we've listed exactly 8 of the divisors. And so there's 8 more to go, 8 more divisor, 4 more divisor pairs. But it's pretty easy to surmise that these are the only 4 digits. Like I'm trying to think of some, you could have what, 222 would be a divisor, right? 333 would be a divisor based on this prime factorization, right? And let's see, what could you do? 303 would be a divisor. Let me just write down a few more. 303 would be a divisor, but it's not 4 digits, right? 202 would be a divisor. See, I'm just listing some of those, but you can see that these are the only 4-digit divisors, which is important here. Any others? Well, whatever. 11 times 101, what is that? Oh, yeah, that's probably 1111. Yeah, 11 times 101 has got to be 1111, right? Any others? 606. How did I get 606, ladies and gentlemen? I did 2 times 3 times 101, which is 6 times 101, which is 606. Okay, so the answer, though, is just these 4. It says how many possible? It's these 4 right here. And so we can come back up and definitively say the answer is 4. Okay. Again, I like that, folks, because it doesn't seem like initially, but once you look at it, a lot of stuff gets eliminated. And the 4-digit restriction gives us the finishing touch on this thing in terms of knowing that we're done with the problem. All right, that's all.